Welcome back. Welcome back to the second video lecture of mine for the subject course entitled Digital Circuit Design. So, what we have studied in the last class, I'll just have a revisit of it. Okay, I'll just have a revisit of it so that you will have a link between the two classes. In the last class, we had just studied about the literals and we have just studied about the basic gates. Basic gates such as AND gate, OR gate, NAND gate, NOR gate, right? So, what are these gates used for? Gates are the basic building blocks of a logic network. Okay, logic network constructed from the gates. How the gates are constructed? Gates are constructed using transistors. How the transistors are constructed? Transistors are constructed using diodes. Diodes are nothing but a simple PN junction, right? So this was a brief introduction. We have studied about the gates and a small truth table, how to write an expression from the truth table, and how to draw a logic network. So this was a just overview of the previous class. So coming to my second lecture class, so in the next few minutes I'll be talking about these particular topics: Minterm, Maxterms, expressing functions as a sum of Minterms and product of Maxterms, canonical forms, standard forms, two-level implementation of standard forms, right? So coming to Minterms, consider a system of three input signal variables. Now, what is a variable? Variable may be X, may be Y, may be Z. X is a variable, Y is a variable, Z is a variable. A term which adds all the input variables either in the true or complement form is called a minterm. I have listed here three input variables minterm. Now here these are the few examples. All the combinations are present over here. If a system is having three input variables x, y, z, what all combinations can be represented? You can represent x bar, y bar, z bar. What is this? 0, 0, 0. X bar, y bar, z. 0, 0, 1. X bar, y, z bar. X bar, y, z bar. Right? What is this? 0, 1, 0. Similarly, up till x, y, z. 1, 1, 1. We can represent the variables, that is variables added together. This is 0, this is 1, this is 2, 3, 4, 5, 6 and 7. 0 to 7. Totally 8 combinations are there. So these are all minterms. Okay, these are all minterms and there are 8 minterms. Each minterm equals 1 at exactly one particular input combination and is equal to 0 at all other combinations. Thus, for example, x bar, y bar, z bar is always equal to 0 except for the combination 0, 0, 0. If the variables x, y, z is having input value 0, 0, 0, then x bar, y bar, z bar will be equal to 1. Its function is equal to 1. Accordingly, the minterm x bar, y bar, z bar is referred as m0. In general, minterms are designated mi, where I corresponds to the input combination. So m0, m1, m2 up till m7 if the system is having three input variables. So this is about the minterms. So minterms also, we are for the three input system under consideration, the number of possible input combination is 2 raised to 3 or 8. That is 3 is the number of input variables x, y, z. There are 3 variables, no? So 2 raised to 3. How many total combinations? 2 raised to 3 is equal to 8. So total combinations are 8. There will be 8 rows here from 0, 0, 0 up till 1, 1, 1. This means that the system has a total of 8 minterms. If the system is having 3 input variable, then total input combinations will be equal to 8. That is from 0, 0, 0 up till 1, 1, 1. In general, for n input variables, the number of minterms will be, the total number of possible input combinations will be 2 raised to n. That's why I told in the earlier slide, if the number of input variables are 3, 2 raised to 3, total combinations will be 8. If suppose the number of input variables are w, x, y, z, 4, that means 2 raised to 4, that is equal to 16. So total number of rows will be 16 if the number of inputs variables are 4. Okay, so a minterm equal to 0 for all input combinations except 1, where minterm is equal to 1. Fine. So what you have to understand here, just see just an example. If a system is having a 5 input variables, number of minterms is equal to 32. So from this slide entirely is, if the system is having n input variables, total number of rows will be 2 raised to n. Next, coming to the Maxterm. Consider a circuit of 3 input signals x, y and z. A term which ORs all the input variables either in the true or in the complement form is called a Maxterm. Now I have listed here, can you see, with 3 input variables, the system under consideration has total of 8 Maxterm. How we have learned in Minterm that if the input variables are 3, x, y, z, then 2 raised to 3 is equal to 8. Similarly, if the system is in 3 input variables x, y, z, then total 8 Maxterms will be there. Here, this is a sum term. What is this? This is a sum term. For 0, how do we write? X plus y plus z in Maxterm. And next, how do we represent 1 in Maxterm? X plus y plus z bar. Okay. Similarly, how do we represent 7? 7 is x, 7 is actually 1 1 1. So how do we write? X bar plus y bar plus z bar. So in this way we represent the sum terms in Maxterms. Okay, each Maxterm equals 0 at exactly one of the 8 possible input combinations and is equal to 1 at all other combinations. So accordingly, what you have to understand from this slide is, for example, consider an example, x plus y plus z equals 1 at all the input combination where, except where it is 0 0 0. Okay, accordingly, how do you represent a Maxterm? How do you represent a Maxterm for 0 0 0? X plus y plus z, and it is referred as m naught, capital M. For Maxterm we use capital M. For Minterms we use small letter m. Okay, in this way we represent the 0 0 0 in Maxterm. 0 is x plus 0, y plus z, x plus y plus z. This is how we write 0 0 0 0 in Maxterm, that is m naught. Maxterm, how do we represent this Maxterm? For 3 input system, the number of possible input combination is 2 raised to 3, that is 8. This means the system has total number of 8 Maxterm. M naught is x plus y plus z. M1, how do you represent? Actually it is 0 0 1, no? For 0 x. Next again 0 y. 1 means z bar. So this is how you represent 1 in Maxterm. X plus y plus z bar. How do you represent 2? That is 0 1 0 in binary. Now in Maxterm, x plus y bar plus z. Similarly up till m7, that is 1 1 1 in binary, but here you represent x bar plus y bar plus z bar. These are all Maxterms. These are all Maxterm. Why do you call this a Maxterm? A system is having 3 variables and all the 3 variables are present in this. So it is a Maxterm. Next, for n input variables, the number of Maxterms will be 2 raised to n. That is, if it is a 3 variable, 2 raised to 3, 8 combinations. So how do you reduce this? Using De Morgan's theorem or truth table, it can be easily shown that the minterm, the complement of minterms is equal to Maxterm for all I is equal to, what is the symbol? This symbol is for all I is equal to 0, 1, 2 up till 2 raised to n minus 1. So now what you understand from this is the complement of minterm is equal to Maxterm. Expressing functions are the sum of minterms. Consider the truth table shown here and the function f. You can see here the function f. Now let's rewrite the table with few added columns. Few added columns are m2, M4, M5, M7. I want to add these all, M2 plus M4 plus M5 plus M7. How do I add it? See now, function of the 0 plus 0 plus 0, it is 0. All the rows are 0 here. 0 plus 0 plus 0 plus 0 is 0. Now here M2 column is 1. All others are 0. 1 plus any 0 is 1 only. Here all the rows are 0. Here 0 plus 1 plus 0 plus 1, it is 1. 0 plus 1 plus 0, it is 1. 0 plus 0 plus 0 plus 0, it is again a 0. 0 plus 0 plus 1, it is 1. So by this truth table, we can write f is equal to M2, M4, M5 and M7. How do you write f? F is equal to M2 plus M4 plus M5 plus M7. Why only these minterms I have written? Because see, you can see here f is equal to 1 for this particular row, that is M2, 0, 1, 0, M2, x bar, y, z bar. Next you can check M4 for 1, 0, 0 row combination, it is 1. So M4. Next for 5, 1, 0, 1, it is 1. So M5. Next you can see f is equal to 1 for the particular row combination, 1, 1, 1. So you have to check f where all 1, f is having 1, you have to check. And that particular minterm you have to write, that is that particular row you have to check. Where first you check where f is 1 and next you check which row it is, and that minterm you have to add it in the f, that is f expression. F is equal to M2 plus M4 plus M5 plus M7. This is how you have to write f expression from the truth table. Next, expressing functions as a sum of minterms. In general, any function can be expressed by ORing all minterms corresponding to input combination at which the function is having value of 1. Now, in the earlier slide, we had seen that wherever f is equal to 1, that particular row you have to consider and write it in the f function. That is what it is written here in this row. The resulting expression is commonly referred as sum of minterms, okay, and is typically expressed as f is equal to summation 2, 4, 5, 7, where summation indicates ORing of the indicated minterms. Thus f is equal to summation 2, 4, 5, 7. Why this I have written? Because f is having 1 in particular row combination 2. F is having 1 where it is 1, 0, 0. F is having 1 where it is 1, 0, 1. F is having 1 where it is 1, 1, 1. So wherever the function f is having 1, that particular row combinations I have written. And what does this symbol indicate? This symbol indicates sum. Okay, this symbol indicates sum. So this is equivalent to summation of 2, 4, 5, 7 is equal to minterm 2 plus minterm 4 plus minterm 5 plus minterm 7. This is how we have to express the functions f as a sum of minterms. Consider the example with f and f bar. Now, students, look at the truth table. Look at this truth table. There is a output column f. There is another output column f bar. F bar is a complement of f. If f is having the value 0, f bar will be having 1. If f is having value 1, then f bar will be having 0. Similarly, you complete this truth table. This is a given example. So, truth table of f bar shows that f bar is equal 1 at I is equal to, that is here for 0 f bar is 1. For 0, 0, 0 f bar is 1. For 0, 0, 1 it is 1. Okay, that is 1. Next, for 0, 1, 1 f bar is 1. That is, you can write here 3. You can see here it is written 3. Right? Similarly, f bar is 1 for 1, 1, 0. That is 6. So, all this 0, 1, 3 and 6 is been written here. 0, 1, 3, 6 we have written here, and this is equal to f bar. So f bar can be represented as m0, m1, m3 and m6. Summation of this f bar is equal to m0 plus m1 plus m3 plus m6, because wherever f bar is 1, that particular row has been considered and written as a expressed as a minterm. And this also can be expressed as summation of 0, 1, 3 and 6. F is equal to whichever minterms are not there here, that will be the f, because f bar and f are complement of each other. So 0 is there, I can't write here 0. 1 is there, I can't write here 1. 2 is not there, so I have to write it in the f. Next here 4 is there, no, so I have to write here 4. 5 is there, no, so I have to write here 5. 6 is there, so we cannot write here 6. 7 is not there, so 7 we have to write here. So this is f is equal to summation of 2, 4, 5, 7. F and f bar are complement to each other. The sum of minterms expression of f bar contains all the minterms that do not appear in the sum of minterms expression of f. The minterms which appear in f bar do not appear in f. This is a simple concept you have to understand, that the minterms which are present in f bar are not present in f because they are complement to each other. Expressing functions as a product of sum. This form is designated as a product of Maxterm and is expressed using the pi symbol. For Maxterm, we use pi symbol, which is used to designate product in regular algebra but is used to designate ANDing in Boolean algebra. Okay, f bar is equal to phi of 2, 4, 5, 7. That is, we use capital M. I had told you earlier only, we use capital M to designate Maxterm. Capital, that is Maxterm 2, Maxterm 4, Maxterm 5 and Maxterm 7. So f is equal to f double bar. Yes, if I break this, f double bar is nothing but equal to f. So m0 plus m1 plus m3 plus m6 whole bar will be equal to m0 bar into m1 bar into m3 bar and m6. That is equal to m0, m1, that is m3 and m6. See students, when I break the bar and change the sign, I break the bar here first, and here it was plus, it became and here, right? So I break the bar and change the signs, break the bar, change the sign, it will become Maxterm, that is m0, m1, m3 and m6. So f is equal to summation of 2, 4, 5, 6. These are minterms, okay, which is equal to pi of 0, 1, 3, 6. Okay, so these are minterms and these are maxterms. Next, if f bar is equal to pi of 2, 4, 5, 7, then it will be summation of 0, 1, 3, 6. From this, what we have to understand is the maxterms and the minterms are complement with each other. The terms which are there present in the minterm will not be present in the maxterm. So here you can see here f is equal to 2, 4, 5, 7. Okay, here this is minterm. Summation means minterm. Pi means maxterm. So 0 is not there, so I have written here 0. 1 is not there, written 1. 3 is not there, so written 3. Next 6 is not there, so written 6 here. In this way, we represent this minterms and maxterms, and we represent the express the functions as the product of sum terms. This is about this product of sums. Expressing functions as sum of minterms or product of maxterm. Okay, students, minterms means product term. For example, input variable, 3 variables are there, x, y, z. So x bar, y bar, z bar is a minterm. X plus y plus z is a sum term. Okay, any function can be expressed both as sum of minterms or a product of maxterm. The product of maxterm expression pi of mj of f contains all the maxterm for all j not equal to I that do not appear in sum of minterms expression of f. What the slide says is that the minterms which are present in the expression f for SOP, that is sum of product terms, are not present in the product of sum terms. The sum of minterms expression of f bar contains all the minterm that do not appear in the sum of minterms expression of f. This is true for all the complementary functions. Thus, each of the 2 raised to n minterms will appear either in the sum of minterms expression of f or the sum of minterms expression of f bar, but not both. Okay, if f is 0, f bar should be 1, it cannot be 0. That is what he is trying to tell. From this slide, students, what we understand is the minterms which are present in SOP cannot be present in POS. So, max terms are complement of minterms. This is what we can learn from this slide. Next, the product of max terms expression of f bar contains all the max terms that do not appear in the product of max terms of expression of f. The max terms which are there in the f cannot be present in the f bar function. Simple. Okay, this is true for all complementary functions. Thus, each of the 2 raised to n max terms will appear either in the product of max term expression of f or the product of max term expression of f bar, but not both. So given an example here, students, you just see here, there is an example given f of a, b, c, d. How many variables are there? 4 variables are there, a, b, c and d. So what is given here? Summation, SOP, sum of product terms, sum of minterms, 0, 1, 2, 4, 5, 7. Derive the product of max term expression of f and the 2 standard form expression of f bar. Since the system is having 4 input variables a, b, c and d, the number of minterms and max terms 2 raised to 4 there is 16. Input variables are 4. So what is the total number of row combinations? 2 raised to 4, that is 16 row combinations will be present in the truth table. Fine. This is a given problem statement. Okay, f of a, b, c, d, that is equal to summation 0, 1, 2, 4, 5 and 7. F is equal to, write the max term. How do you represent? See, I had told you earlier only, the terms will be there in the max term which are not present in the sum term. So 0 is present. So these are all the min terms which are not there in this. That will be the max terms. Simple, students, it's very simple. 0, 1, 2, 4, 5, 7 are the min terms. From this, write the max term. If I give a problem saying that these are the min term, from this you write the max term. What do? You just write the terms which are not present in this summation expression. So you just write the terms 3, 6, 8, 9, 10, 11, 12, 13, 14, 15. These are the max terms. What are these? Max terms. This is SOP. This is POS. SOP stands for sum of product terms. This is pi. What is this? Product of sum. Product of sum, that is POS. Okay. Summation means SOP, sum of product terms. Pi means POS, that is product of sum terms. Next, F bar of summation. F bar. So here, just see here, 0, 1, 2, 4, 5, 7. This is F. Write the F bar. F bar. F bar contains the terms where F is not having. Okay, F bar contains the term where F is not having. F is having 0, so don't write here. F is having 1 and 2 also, so don't write. 3 is not there, no? So that will be definitely present in the F bar. Okay, 3. Then 5 is present, don't write. 6 is not present, so write it. 7, it is there, so don't write. So 8, 9, 10, as it is a 4 variable, up till 15 will be there. 4 variable, na, A, B, C, D, 2 raised to 4, 16 combinations will be there. So 0 to 15. So upon this, 8, 9, 10, 11, 12, 13, 14, 15, all I have written here. So this is F bar. What is this? F bar. F bar is complement of F. So F bar of, so you can also represent in terms of max terms. Max term is product of sum terms. So F bar is equivalent to pi of summation only, 0, 1, 2, 4, 5, 7, because I had told you max terms are complement of minterms. So max terms are complement of minterms. F of summation, F of summation, that is F of summation is equal to F bar of pi. Once again, I'll tell you students, F of summation, F of summation, this is sorry, F of summation is equal to F bar of pi. So whatever the terms are present here, the same thing will be presented the F bar of pi. Okay. So next, here I have an example. Okay, students, just see here. F of ABC is equal to AB plus A bar C. Expressed F as the sum of min terms. Now let me tell you. Okay, AB is a product term but not a min term. Why? Because C variable is not present here. I repeat students. AB is a product term but not a min term because C is not there. C is not there. Next, A bar C is a product term, but variable B is not there. Hence, it is a product term, but not a min term. Okay. So here, F of A B C is equal to A B. Here C is not there. C plus C bar. We can write it plus A bar C. B plus B bar. So I am trying to express it in the sum of min terms. This is not in the min term form. It is in the SOP form. This is a sum of product terms, not sum of min terms. So C is not there. Just write here C plus C bar plus A C. B is not there. Right here B plus B bar. So just multiply this ABC plus ABC bar plus A bar BC plus A bar B bar C. So see here 0 0 1 I have written here. Next 0 1 1 3 I have written here. 1 1 0 I have written here 6. 1 1 1 I have written here 7. Okay. In this way you can write it in the form of sum of min terms. Students, I repeat once again, AB is a product term, not a min term because C variable is missing. A bar C is a product term but not a min term because B is missing. Okay. Now I have to express in this in the min term means I have C is not there, no, C plus C bar I have to write. This I want to express it in the min term, no, B is not there, no, so I write just B plus B bar and just multiply it and then give it in the shape of sum of min terms. Shortcut method, student, just see AB is equal to 1 1. This gives us the input combination 1 1 0. Here your dash is there, no, dash can be 0 or 1, that is 1 1 0 or 1 1 1. This which corresponds to M6 and M7. 1 1 0 is M6, 1 1 1 is M7. Next A bar C, that is A is 0, B is not there, so don't care. C is there 1. This gives us the input combinations 0 0 1 and 0 1 1. Dash can be 0 or 1. 0 0 1 it is M1. 0 1 1 it is M3. So here you can see 1 3 6 7. Similarly we have got here 1 3 and 6 7. This is also a shortcut method to represent it in the sum of min terms if it is in the sum of product terms. Operations. The AND operation on two functions corresponds to the intersection of the two set of min terms of the functions. The OR operation on two functions corresponds to the union of the two sets of the min terms of the functions. Okay. Students, listen here. There's an example. Okay. Let f of ABC summation m is equal to 1367 and g of ABC is equal to summation m of 0 1 2 4 6 7. There are two functions given, f of ABC, g of ABC. Now I have to multiply these two. Okay, f I have to multiply with this g. So see here, 0 is there in both, no, so it is, we should not write it. 1 is there in the both, in f expression also it is there, g also it is there, so write 1. 2 is there in the both, no, so don't write. 3 is there in the both, no, so don't write. 4 is there in the both, no, don't write. 5 not there in the both. 6, both expressions, f expression and g expression are having both 6, so write 6. 7, yes, f and g both are having 7, so write 7. Okay, so here both are having 7, so write 7 here. Okay, so the common terms which are there in the f and g is nothing but f into g. F plus g, you have to just go on adding. 0 is there, yes, in any one just add. 0 is there, then write. Next 1 is there, then write. 2 is there, write. 3 is there, yes. 4 is there, just write it. 5 is not there in the both, so you cannot add it. Next 6 is there, yes, write it. 7 is there, so write it. In this way we can just say that f plus g we can write. Okay, similarly we can write f bar into g. Okay, we can write f bar also, and we can write f into g also similarly. Okay, next, canonical forms. See students, there are two types of canonical forms: sum of product terms or product of sum terms. Sum of minterms and the product of maxterm forms of boolean expression are known as canonical forms. Canonical forms are also called as irredundant disjunctive formula, irredundant conjunctive formula. So canonical expressions can be of two types: sum of product terms or sum of product of sum terms. SOP or POS, these are the two forms of canonical. Two functions are said to be equal if and only if they have the same sum of minterms and the same product of maxterms. Students, here one of the example is solved for you. F1 is equal to a bar into b bar plus ac plus bc bar, and f2 is equal to a bar c bar plus ab plus b bar c. If both are equal, you just solve it on your own and you will get that summation f1 is equal to summation of 0 1 2 5 6 7, f2 is equal to summation m of 0 1 2 5 6 7. Since f1 and f2 are containing the same minterms, we say that both the functions are equal because they contain the same set of minterms. Next, standard forms. A product term is a term with ANDed literals. Thus, AB, A bar B, A bar CD are all product terms. A minterm is a special case of the product term where all the input variables appear in the product term either in the true or complement form. True form, if for example, if I consider x, x is a true form. Complement form, x bar is a complement form. A minterm is a product term in which all the variables appear either in the true form or complement form. Okay, a sum term is a term with odd literals. Thus, a plus b, a bar plus b, a bar plus cd, these are the examples of the sum terms. A max term is a special case of sum term where all the input variables either in the true or in the complement form are odd together. A max term is a sum term where all the input variables appear in the true form or in the complement form. Boolean functions can generally be expressed in the form of a sum of product or in the form of a product of sum. So canonical forms, I told you know there are two types, SOP and POS. So Boolean functions can be represented either in the sum of product term or in the product of sum terms. A sum of minterms form is a special case of the SOP from where all the product terms are the minterms. Okay, the product of max term form is a special case of the POS form where all the sum terms are max terms. The SOP and POS forms are standard forms for representing Boolean functions. Okay, this is a two-level implementation of standard forms. Standard forms are SOP and POS, sum of product terms and product of sum terms. Any SOP expression can be in two level of gates. The first level consists of the number of AND gates which equals the number of product terms in the expression. How many AND gates will be having, students? Students, just listen here. How many AND gates will be having? AND gates is equal to the number of product terms present in the expression. Each AND gate implements one of the product terms in the expression. Like for example, XYZ. XYZ requires 3 input AND gate. X bar, Y bar, Z bar. So this also requires 3 input AND gate. So one product term, one AND gate. The second level consists of a single OR gate whose number of inputs equal the number of product terms in the expression. If suppose you have a xyz plus x bar y bar z bar, then you require 3 input AND gate and 2 input single OR gate. Okay, that is what here it is told in this particular slide. Example, implement the following SOP function. So function is given here, f is equal to xz plus y bar z plus x bar yz xz. See here, 2 input AND gate xz, which gives us the product term xz. Y bar z, see here, y bar into z, which gives the AND gate product as y bar z. Next 3 input AND gate, that is x bar y z. So this gives me 3 input AND gate and output is x bar y z. These SOP, these are ordered together, these are all product terms. How many number of product terms? 1 2 3. So how many AND gates? 1 2 3. So these all products are ordered together. So here you can see the output of AND gate is given as an input to OR gate. Here also it is given as an input to OR gate. Here also it is given. So first level we have and in the second level we have OR. It is sum of product terms. Students, please understand through this example. We are implementing a SOP function. These are the product terms and we are ORing it. Hence it is SOP, sum of product terms, implemented in 2 levels, level 1 and level 2. Level 1 contains only AND gates, level 2 contains OR gate. Next, 2 level implementation of standard forms of product of sum expressions. Any POS expression can be implemented in 2 level of gates. First level consists of number of OR gates which equal the number of sum terms in the expression. Each gate implements one sum term in the expression. The second level consists of a single AND gate whose number of inputs equals the number of sum terms. Students, let us understand through an example. Implement the following product of sum term. This is a product of sum term. Can you see here? This is a sum term. This is also another sum term. This is also another sum term ANDed together. So it is a product of sum terms. Product of sum terms. X plus Z. How do you implement this? You require 2 input OR gate. See here, X plus Z. How Y bar plus Z? How do you implement it? Again 2 input OR gate. Y bar plus Z. Next, how do you implement X bar plus Y plus Z? Again 3 input OR gate, X bar plus Y plus Z. In the first level we have OR gates. In the second level we have AND gate, ANDed together. So product of sum terms. What we have implemented here? Product of sum terms. Any expression can be implemented in 2 levels, level 1 and level 2. Right, students? So this is an example for implementing product of sum terms. Thank you, students. We'll meet in the next class with the next video lecture. Thank you.